So hi, my name is Hugo, and pretty happy to be here and to have the opportunity to give that talk on site. So thanks, Volkan and Jan. So today I'll be telling you essentially how the generalization ability of kernel method largely depend on two numbers which characterize your dataset, and I'll tell you more about that in a couple of slides. And first, these are the two references of the papers this talk is based on. And let me just find a way to, this is this one. Okay, this is joint work with Bruno Loureiro, Florent, and Lenka, Zeborová, all of whom are currently at EPFL. So if you have a data set with covariate x mu and labels y mu, which can either be real numbers if you're interested in regression, or plus or minus ones if you are looking at a classification task. One way to learn the data set is to use a staple of the machine learning toolbox, namely kernel methods. And so kernel methods still outperform neural networks in some tasks, and also they constitute an interesting theoretical limit of neural networks. You all heard of NTK, for example. So a quick refresher of what it means to be learning a data set with a kernel. Well, take your covariate x mu, and you plug that in what's called the kernel feature map psi. So this is a function that takes your data, sends it to a high-dimensional space in a nonlinear fashion, thereby giving you some expressivity. And once you transform your data x into these features psi of x, well, it can just fit a linear model by doing empirical risk minimization. So you minimize this loss L with some L2 regularization of strength lambda. And we'll be looking more specifically at the case of a square loss if you're looking at regression. So we're doing kernel ridge regression. And also hinge loss if you're looking at the classification task. So we'll be interested also in kernel support vector machines. So that was a one-slider on kernel methods. So how good your kernel method actually learns the data set, well, is measured by its generalization error, which is for regression the mean distance between the true label and what your model predicts, squared. And for classification, it's the probability that your model makes a mistake on a fresh test sample and wrongly labels a fresh test sample. Of course, the more samples you have in your train set, the more information you give to your model, the better it learns, the smaller its prediction error. So the more samples there is, and the smaller the generalization error, and the generalization error will decay with the number of samples. We'll be more specifically interested in the rate with which this error actually will decay. And more specifically, can we come up with a formula describing this rate? And if so, on which features, which characteristics of the dataset will this rate actually depend? I give the answer in 2 slides, but first let me say that we are building our analysis on the previous work in a non-rigorous fashion. We're applying a theorem that we had and a different asymptotic limit. But part of the result have been proven in a later work by another group in 2022. So while the whole talk is not fully proven, a part of it has been put on rigorous grounds. So the first assumption which we'll be needing is that of Gaussian design. So remember those transformed data into these features living in this high-dimensional space, psi of x. Well, we'll assume that their distribution looks approximately Gaussian, which sounds like a strong assumption, but I show you some plots and some results that hint that our result actually hold beyond the Gaussian case, and there's some universality hidden behind all this. The second assumption is just the generative model. I have to tell you how the labels are created, right? So we'll assume that the kernel is expressive enough so that the labels are just a linear combination of the features. More specifically, we'll assume the existence of a teacher vector theta star, so that in the case of regression, your labels y mu are just given by the scalar product between this teacher theta star and your feature psi of x mu, plus some additive Gaussian noise of strength sigma. In the case of classification, the labels plus or minus 1 are just given by the sign of the scalar product between the teacher and the feature. So that plans a bit the setting the model will be looking at, very simple and quite natural. And the other 2 assumptions which we'll be making on the dataset are quite well known in statistical learning theory and go by the name of source and capacity conditions. So I try to provide some intuition about what those actually mean in that slide. So the capacity condition essentially assumed the existence of a real number alpha, which is basically the rate of decay of the eigenvalues of the feature covariance. So what does it mean? Well, if you have a large value of alpha, it means that there are only a small number of eigenvalues which have reasonable value and a lot of small eigenvalues. So that means that your data essentially lies along a small number of directions, and the distribution will be very narrow along all the others. So effectively, the data will look more or less low-dimensional and will be a very simple data distribution. Conversely, if you have a small alpha, it means that your data is spread along a large number of directions, therefore it will look more higher dimensional, and therefore it will be a more complex data distribution. So alpha, you should think of it as a parameter that captures and gives you a measure of the complexity of the data distribution. At the same token, the source capacity introduces another parameter R, which captures the complexity of the teacher, or of the target function which generates your labels. If you have a large R in feature space, the teacher vector will be well aligned with the main direction of your feature distribution. It will be easy to recover. It means that the target function which is generating your labels is very smooth. It only depends on a small number of features. It's very easy to recover. Conversely, if you have a small r, it means that the target function which you're trying to learn is very wiggly, very rough, and much more complex to learn. In terms of the teacher vector, it's less aligned with the main directions of your feature distribution. So this alpha and r really just are two numbers that subsume, that measure how complex the learning task is, how complex the labels and the data distribution actually are. So as we'll see, it's possible to characterize the rate of decay of the prediction error for kernel method in terms of those two numbers. Because how fast the kernel method learn will depend on the complexity of the learning task as more or less measured by those two numbers. So in the next part, I'll treat kernel regression. And then at the very end, I'll also speak about classification tasks. So analyzing the rate of decay for kernel method is quite a natural question and has been already studied quite extensively in the literature. But the fun thing is that some years ago, depending whether you looked into the statistical learning literature, here a sample of some relevant papers in purple, or in more statistical physicsy literature here in green, you would end up with finding different values, different expressions for that rate, without being able actually to find an explanation why there is this discrepancy. It's a case of worst case analysis versus typical case analysis. Is one case noisy, the other not? So we wanted to bridge that gap and provide a unifying picture of what you can observe in kernel regression. So we find that you can have 4 possible observable rates, for the decay rate of the generalization error when you learn using a kernel method. And which of these 4 rates you actually observe depend on how large is your train set here on the x-axis, and how much you regularize here on the y-axis. For example, you have a small number of samples and you regularize very little. You end up in the green regime and you will observe a decay rate of 2 alpha, mean r and 1, where alpha and r, as a reminder, are the capacity and source coefficients. Just to make contact with the literature, some of these rates were already present in some form or the other in the literature. For example, the statistical physics papers derive this green rate, while the purple dot correspond to the well-known work of Capineto and De Vito. Interesting thing is, some of these references are actually worst-case analysis. They derive the same rate, same rate as our, is good? Yeah. As our Gaussian typical case analysis in a worst-case analysis, meaning that there is some universality hidden behind that, since we're able to recover that using a Gaussian assumption. So this Gaussian assumption doesn't seem to be too harmful. The second good observation that pops up from our analytics is that, remember, there was this label noise that was corrupting the labels in the case of regression. Well, it really doesn't have an effect in two of these regimes, namely the blue and green regime. So everything happened just as if the learning task was completely noiseless. So therefore, the learning task is particularly easy, and in these two regimes, you will observe a fast decay rate because it's easy to learn. Conversely, the noise has an effect in the other two regimes, the orange and the red. The learning task is effectively noisy, and therefore these two regimes are characterized by a much slower decay rate. And you can actually see that on learning curves. So when you have a small train set, you find yourself in either the blue or green noiseless regime, and therefore at the beginning you learn very fast. The learning task is effectively noiseless, and you see that the error decay is very fast. But at some point, as you increase the number of samples, you're crossing over to one of those two noisy regimes, either red or orange, and you'll observe that slowdown of the decay for the generalization error. And that's held also for a blue to orange crossover. So you really observe that slowdown of your learning speed. So these are some simulation of artificial Gaussian datasets where the dashed lines correspond to the theoretical values of the rates and the dots are simulations. I just wanted to provide some intuition about why that kind of crossover phenomenon from a noiseless regime with fast decay rate to a noisy regime with slow decay rate actually happened. And it has to do with what's called in the literature benign overfilling. For example, we'll look at these two papers. So remember that the covariance had this power law decay for the eigenvalues. The spectrum was comprised of some so-called heavy dimensions where the eigenvalues are quite large, and the data will be quite spread and has quite a large variance along these directions, and a myriad of small variance directions along which the data distribution is very narrow, which are sometimes called light dimension. So what happens when you have a small number of samples and you find yourself in, for example, the green regime, is that, well, you just use these very small components of your data, the light dimensions, to just overfit your noise. And since the components are very small anyway, they don't matter so much for the generalization error, and as long as you generalize well on the important direction, namely the heavy dimensions, well, your generalization is not too bad, and you have overfitted the noise. So you have sort of hidden all the noise inside this light dimension without hurting your generalization ability. So that's why you don't actually observe the noise when you have a small number of samples. But if you go to larger number of samples and your error decreases and decreases, at some point for your error to decrease further, you actually need to generalize well also on those lighter dimensions. And then you have to deal with the noise, and that's why the learning task becomes more complex and you have this slowdown of the decay rate for the generalization error. Same thing happens for the other type of crossover. And just last slide on the case of regression, I just wanted to show you that remember we had this assumption that the data distribution was looking Gaussian more or less. While it doesn't matter, I mean, it does matter, but sometimes our result also hold beyond the Gaussian case. So these two plots are for real data sets, fashion MNIST and MNIST, which we take for the sake of the experiments as regression tasks. And so dots correspond to simulation. We're just running kernel ridge regression using two standard kernels. This, on the left, is a polynomial kernel, and on the right is RBF kernel, Gaussian kernel. And on the other hand, we take the data set and we measure those two coefficients. You remember this alpha and R, source and capacity coefficient. We measure them on the data set. We plug that in our theoretical formulas, and we compute the semi-theoretical rates which we expect to observe, and these correspond to the dashed lines. So on some of these real data sets, not all, the agreement is actually pretty good, and furthermore, in this fashion MNIST dataset, you can see pretty clearly that kind of crossover from a fast decay to a slow decay as you cross from a noiseless regime to a noisy regime. So yeah, it doesn't hold for all the real dataset, but for datasets which are reasonably described by these source and capacity conditions, these actually hold. So this class of data sets described by source and capacity are quite interesting because they do comprise some real data set. And some, I think I'm good on time, right? Some words. Okay, some words on kernel classification, which correspond to this paper here, which you can find on arXiv. Well, you can just basically repeat the same analysis and derive some formulas for the rate for some classifiers. For example, this is kernel max margin support vector machines. And on the right, you see some plots where we just check that on artificial Gaussian datasets, where the dots correspond to simulation and the dashed lines correspond to the theoretical rate. Interestingly, we didn't find, to the best of our knowledge, existing rates in the literature. The best we found was a rate by Chrisman and Steinwerth in 2008, bounding the error rate of support vector machines in the worst case. And as you can see, it really fails to describe tightly the decay rate for datasets which are described by the source and capacity conditions. So it's a worst case rate, but it seems that it's quite loose in this case. And does not describe this class of datasets, which again is quite interesting because some real datasets are actually falling in this category of datasets. So we're improving on that in our analysis, and we also provide the rates for another classifier, which is oftentimes used, the rich classifier, so you minimize the square loss in a classification setting. Again, simulations are dots, and dashed lines are the theoretical value. Last couple of plots, and then I'll be done, are again some real data plots. So we just wanted to check if this theory could also hold beyond the Gaussian data distribution case. Well, here are some plots for Cypher10 and Fashion MNIST, again some standard kernels. Again, dots are simulation. Dashed lines are semi-empirical rates where we measured this alpha and R on the data sets and plug that in our formulas. And as you can see, the agreement is pretty satisfying. Just the summary slides. For kernel regression, we're providing a unifying big picture of 4 possible regimes which can observe, thereby bridging the gaps between existing studies. We characterize also noisy versus noiseless regime, which regimes the noise actually has an impact and which regimes it can completely be forgotten. And we discuss the crossover phenomena from one noiseless regime to one noisy regime, and observe them also in some real data sets. And for classification, we compute rates also for this class of data sets described by source and capacity, show that it's a better description than known worst case bounds, and we show how they're relevant also for some real data sets. And I thank you for your attention.